All right, so now welcome to the last part of this lecture. So we're now going to the concept called the single cycle architecture, right? So what is single cycle architecture? Basically, if you look at the ISA, right? The ISA are what's visible to the programmer. These are the state of the hardware, right? These are the state of the hardware that the programmer can see and they can control. We call this architectural states. Things such as the name of the register, right? R0, R1, EAX, EDX in x86, right? The value inside this register, the program counter or the instruction pointer, which is basically what store the address of the line the CPU is running on right now, right? These are something that programmer can see. The memory, right? The storage location indexed by an address. These are what the programmer can see as well. They can control that, they can see that, they can program using these tools, right? Programmer can directly see and handle the values. But then this is where the interface ends, because there's also the internal state that are not visible to the programmer. This is called the microarchitectural state. This is called the microarchitectural state. There's no way for the programmer to access this. What are the microarchitectural states? Things like, what are the values of certain cache blocks inside my hardware? Well, what are the intermediate value of the register in the middle of the 5-stage pipeline, right? So for those of you who went through computer engineering or computer science degree, you might have heard about the 5-stage pipeline. You might have learned about it sometime while you're taking the class, right? Inside the 5-stage pipeline, from the programmer point of view, you have no way to control anything in there, right? You only know at the end of the instruction what happened to your register, right? So now that we have the ISA give you the method, right? The method to command your computer. The hardware itself is the microarchitecture, right? Basically, it connects all the electronic circuits together, and it allows the machine to interpret these method, right? This method from the ISA. So let's say you start with architectural state 1, AS1. You start here, right? You run one line of assembly. What happened? Basically, assembly that you write change the state from AS1 to AS2. That's all. That's all. What happened when you have the ISA and run one line in assembly? You start with a state. You move to the next state. And what are our expectations of this? The ISA, right, will specify what the second state, the next state should look like. How it should look like if you give them the instruction and the AS1 and the AS1. What's missing here? Anyone want to guess what's missing here? So what's missing is, from the programmer point of view, you don't know what happened. How do you get to AS2? What are the hardware? What are the hardware that allow you to move from AS1 to AS2? So that's the microarchitecture. Basically, these are the hardware inside your CPU that run the instruction, right? That change from AS1 to AS2. And there can be any number of these intermediate steps in the middle. These are design choices, right? As computer architect, I can build a hardware that allow you to go from AS1 to AS2 in one clock cycle. I can also build a different hardware that go from AS1 to temp1, temp2, temp3. Programmer never see that. And then you arrive at AS2 in multiple clock cycles, right? In multiple clock cycles. These has trade-off. These has trade-off. So Anyone want to take a quick guess on what would be the trade-off here? So what are some of the obvious trade-off? How many cycles does it take for me to go from AS1 to AS2 in the second model with multiple clock? How many cycles do I have to spend? Can someone tell me how many cycles do I have to spend to go from AS1 to temp1, temp2, temp3, and AS2? And each arrow is one cycle. Each arrow there is one cycle. So how many cycles is that?
4.
4. Yes, thank you. Right. How about the first one, AS1 directly to AS2? How many cycles is that? 1, right? You may be wondering, which one seems better now? So which one seems better?
First one.
The first one seems better, right? But now let me tell you this. What if whatever I do in here in the second case, right? Whatever I do in here, make it such that I can have the CPU with 4 gigahertz, comparing to this where there's nothing I can do. Everything that built there from in a case where I have to go from AS1 directly to AS2, there are certain long wires, so long to the point that my clock can only go up to 500 megahertz. I can only clock my CPU to 500 megahertz. While the second case, right, I need to spend 4 clock cycle, but each cycle, I can clock it at 4 gigahertz. Which one is now better? Which one is now better?
Below.
The second one, right? Now the second one is better, right? So most of the time, if I need to add the number of clock cycle, it's actually there so that I can break these long wires in your CPU, right? Everything is electronics circuit, right? This thing run using wires, actually สายไฟอะครับ คือมันเป็นสายไฟในนั้นจริงๆ so if we can break these long wires and long circuits, long logical components into much smaller and simpler block of things, and I transition from one state to another, I can actually make it such that each clock cycle is a lot smaller. ก็คือถ้าผมสามารถปรับวงจรอะให้มันแบบตัดสายไฟตรงกลางให้มันเป็นสเตตอะมันอาจจะทำให้คล็อกได้เร็วขึ้นเยอะมากๆก็ได้ ซึ่งนี่คือเรื่องจริงที่เกิดขึ้นใน micro architecture นะครับมันเป็นสาเหตุที่ทำไมเราถึงสามารถคล็อก CPU ได้ที่แบบ4กิกะเฮิรตซ์5กิกะเฮิรตซ์ก็ได้เหมือนกัน
clock cycle คืออะไรนะครับ
คำถามที่ดีครับ clock cycle เนี่ยก็คือเราพูดถึงstate ใช่ไหมครับไอ architectural state ก็คือ state ที่โปรแกรมเมอร์จะได้เห็นใช่ไหมว่านี่คือผลลัพธ์จากการ run instruction ใช่ไหมครับ clock เนี่ยมันคือการเปลี่ยนจาก state หนึ่งไปอีก state หนึ่งทุกครั้งที่ผมต้องการเปลี่ยน state ก็คือผมต้อง clock เหมือนแบบให้มอง clock เป็นแบบนาฬิกาที่แบบผมทุบโป๊ะแล้วมันจะหยุดเวลาโป๊ะหยุดเวลาแล้วระหว่างที่มีการทุบแต่ละครั้งคือเซอร์กิตมันจะ move อิเล็กตรอนก็ move ปุ๊บแล้วผมเคาะโป้งมันก็จะหยุดแล้วผมสามารถดูได้ว่าตอนเนี้ยอิเล็กตรอนอยู่ตรงไหนค่าอยู่ตรงไหนเก็บอะไรไว้ตรงไหนบ้างมันเป็นสเตทแล้วผมต้องมีคล็อกเพราะว่าถ้าผมไม่มีคล็อกผมไม่สามารถบอกได้เลยว่าไอ้โค้ดที่ผมรันจากตรงนี้ไปถึงตรงเนี้ยผมจะหยุดตรงไหนมันเป็นการเหมือนเป็นเกจไว้ให้เรา move ในหน่วยเวลาครับ
โอเคครับ
เห็นภาพขึ้นไหม
ครับ
สมมติผมจะรันโปรแกรมผมต้องคล็อกมันเพื่อให้บอกว่ามันจะได้ proceed แต่ละสเต็ปได้ แต่ว่ามันก็จะมีบางกรณีที่มันจะบอกว่าผมสามารถคล็อกได้เร็วแค่ไหน ตัวอย่างเช่นถ้าผมนึกตีต่างเอาว่าแต่ละครั้งที่ผมต้องคล็อกผมต้องแบบสามารถก้าวได้อย่างต่ำ19แบบเดินเนี่ยปุ๊บ19ใช่ไหมจะ929ก็ได้ถ้าผม929แล้วผมจะคล็อกก็นับเหมือนกันถือว่าเป็น1คล็อกได้เหมือนกัน อันเนี้ยข้อจำกัดของผมคืออะไร คือเวลาที่ผมคล็อกที่เร็วที่สุดที่จะเป็นไปได้คือ เวลาที่กล้ามเนื้อผมจะสามารถดึงเท้าผมจากตรงเนี้ยเพื่อก้าวไปไออันเนี้ยอินเทอร์วัลตรงเนี้ยผมไม่สามารถคล็อกได้เร็วกว่านี้ได้เพราะว่าถ้าผมคล็อกเร็วกว่านี้ผมยังก้าวไม่เสร็จสายไฟก็เหมือนกันในระบบเซอร์กิตทั้งหมดใช่ไหมครับถ้าผมจะต้องการคล็อกเนี่ยแปลว่าทุกอย่างที่ผมจะทำให้เกิดขึ้นระหว่างแต่ละไซเคิลมันไปอยู่ใน stable state แล้วมัน stable พอที่ผมจะสามารถวัดค่าทุกอย่างได้เพราะฉะนั้นถ้าผมคล็อกเร็วเกินไปเกิดอะไรขึ้นครับ
พอ
ถ้าผม
จะ
คล็อกเร็ว
ไม่
เกินไป
เสร็จนะ
อ่ะใช่ครับ คือลอจิกบางตัว มันอาจจะใส่ไฟยาวมาก หรือว่าลอจิกมันคอมเพล็กซ์มากๆ มันยังไม่เสร็จ คืออิเล็กตรอนที่แบบควรจะไปอยู่ตรงผลลัพธ์ท้ายสุดมันยังไปไม่ถึง แล้วถ้าผมคล็อกไปแล้วผมจะคล็อกเร็วไป เสร็จแล้ววงจรจะบั๊กอันนี้คือวงจรบั๊กจริงจัง คือน้องจะได้คำตอบที่แบบไม่สเตเบิลตอบไม่ได้เลยเดี๋ยวซ้ำมันจะเป็น0หรือมันเป็น1เพราะมันยังงงอยู่ มันยังกำลังรอไปอยู่ที่ steady state เพราะฉะนั้นเวลาเราคล็อกเนี่ยมันจะเป็นตัวกำหนดว่าเราคล็อกได้เร็วแค่ไหน คือถ้าวงจรยิ่งคอมเพล็กซ์มากๆ ผมก็จะคล็อกได้ช้าลง โอเค เห็นน้องพิมพ์น้องปิมพยายามพิมพ์อยู่มีคำถามอะไรป่ะครับ เปิดไมค์ได้นะ อาจจะรออ่ะเดี๋ยวงั้นเดี๋ยวขอ move on ก่อนนิดนึงก็ได้ ระหว่างรอคำถามนะครับ All right, so let's move on a little bit. So I'm gonna show some highlights into now. Before that, let's go over some background, right? A few backgrounds that I would like to talk about before we proceed further, because I might talk about these terminology, and you might not have heard about it, especially if you did not go through the computer engineering degree, right? So there's this thing called combinational logic. Combinational logic are a set of logical operation like and or that when you put together, right, it represents some kind of computational based logic, and it happened within one cycle. There's no time element here. Sequential logic, as the name suggests, is a logical operation and logic that you put together in the hardware that can represent sequence of things that happen through time. So the sequential logic would have a way to dictate this would happen at time number 1. Then it shifts to time number 2 here, and it shifts the state to time number 3. So that's sequential logic. Clock, I just explained. Clock is kind of like the amount of time that you need to enforce to make sure the sequential logic would operate and perform the operation that might be based on some combinational logic so that it changed from state 1 to state 2. Critical path is the longest path in your circuitry diagram within one clock cycle that determine how fast your clock have to be. Right. So these are background. If I refer to some of these terminology, basically here are the definition I just explained, right? And now let's look back at the single cycle processor. Basically what we want to do is, because it's single cycle, we want a processor that compute every single instruction in one clock cycle. I have AS1. It went through some combinational logic to transform my data to AS2. Then I want to go through my sequential logic to save the state. And then I clock. When I clock it, the sequential logic would actually allow me to show AS2, not AS1. So what determines the critical part of our combinational logic is the longest, right? The longest wiring that happened in my combinational logic right here, that I would need to make sure to hold the value so that if I have electron coming in, it propagate and arrive at the sequential logic so that I can make sure I have a steady state and I can clock it as I mentioned earlier. Right? So that's the critical part. And in a single cycle processor, the downside of this is if I have to support 100 different instructions, the slowest instruction would determine how slow is my clock cycle. So if my instruction want to access memory, for example, this would take hundreds of nanoseconds, right? Adding, multiplying takes only 1 or 2 nanoseconds, but it has to wait for the instruction that access the memory. So now every single instruction have to be hold off until I can guarantee if I have a load instruction, it also takes 100 nanoseconds, and it has to make sure it passed that. If I have instruction that process an IO instruction, that's even worse. Like you're talking about microseconds or milliseconds. And you probably don't want a 1 kilohertz processor, right? But let's now study how I can build it, right? For now. Question is, well, how do you measure performance and what happened in one cycle, right? So instructions are processed in steps, basically. So recall back from lecture 1, right? Instructions are in memory. So the step is, first, if my program is in the memory, the first thing I have to do, I need to go and get my instruction, fetch the instruction. Then after I fetch, I just got random bits like 1, 1, 1, 0, 0, 1, 1. I don't know what that means yet. The next thing is I need to decode the instruction. Now those ones and 0 turns into, for example, add 0, 1, and 2. Then I would evaluate the address if I need to get the address, or if I need to get the operand, I go get the operand. In this case, R0, R1, and R2, right? And then I execute, I run them. And then afterward, I would just have to store the results back. So this is what happened in one cycle for a single cycle processor, right? Note that not every single instruction requires all the steps here. If it doesn't have to go to the memory location, it doesn't have to evaluate the address. If it only have to fetch one operand, it would only fetch one operand, right? So this is what happened with single cycle instruction. Everything here has to happen in one single cycle, right? The next thing I want to talk about is data path versus control logic, because this is something that we might talk about in the future. I might refer to. So when you process one instruction, it transforms the data from D1 to D1 prime, right? Think of it as a math function like add, subtract, multiply, right? You transform them from D1 to D1 prime. This is done to functional unit like adder, multiplier, right? The instruction will tell you what the operation is. And then you process instruction with two main components. The data part is the hardware that deals with the operation itself, the one that transforms D1 to D1 prime, like adder, which would be functional units, the storage, right? The actual structure that move the data around, like wires, right? Or mux or demux, right? The control logic are the signal that the CPU used to control every single piece of your data path. As the name suggests, it's a logic that control your hardware. Things like what data goes into the inputs here, what should we read from the register. So these are the control logic, right? And we'll go with our toy example. We'll actually finish here in our toy example, right? So the program counter, and we will resume the lecture next week with the toy example, so that hopefully it's more clear. The first thing you have is the instruction register, or PC. This tells you what line you are trying to read from, right? What line in the program you're running. Whatever value in here is the address to your DRAM, to your main memory. It go and check your memory. Okay, this is your program, right? This is your program. It go to that address. It fetch that instruction, whatever that program is, right? This line right here gets fetched to your decoder. So this is going to be like 11101, like a bunch of combination of ones and zero. It gets fed to the decoder. Decoder figure out, okay, that might be, say, an add operation, right? So if it's, say, add 0, 1, and 2, now you figure it out through the decoder. Decoder would trigger the select line to all the components saying, hey, I want R1, I want R2. I want to send R1 and R2 into my adder. If you need to get something from the memory, there's also the data part there as well. But in this case, it's just adding two numbers, so we don't need that. We perform the add, the decoder enable the adder. The adder send the results back, right, to, again, the register file. We write the result back, right? Then you update the program counter. If you're not jumping, right? If you're not jumping or anything, right? The next PC is going to be PC plus 4, which is the next line of your code, right? So we are going to resume, right? We're going to go and resume this toy example. But before we go there, let's start with our toy ISA. Let's say we are using a 16-bit processor, really, really simple ISA with 8 register file, right? It means that if the RS, like the source bit, is 0, 0, 0, this is R0, 0, 0, 1, this is R1, 1, 1, 1 is R7, right? And then I use 3 address machine. I support source 1, source 2, and destination. So I can do something like add R0, R1, and R2. These are like legit operation. What do we need? Like things like opcode bits and the bit that represents source 1 and source 2 and destination, and the immediate bit, right? And remember, we're defining our own ISA. We're not like taking the x86 or ARM or RISC-V. This is our toy ISA for this class. So I'm going to define it like this. If I do compute instruction, the first 7 bits here would be the opcode. And let's say the opcode for an add is 0, 0, 0, 0, 0, 1, 1. And let's just go with that for now, right? And if I want to do add R0 into, basically I want to add R1 plus R2 and write the result into R0. So R1 is source 1, R2 is source 2, R0 is destination, right? And I just said opcode for the add is 0, 0, 0, 0, 1, 1. So what is the binary for this instruction? This part is 0, 0, 0, 0, 0, 1, 1, right? Source 1 is R1. R1 is 0, 0, 1, number 1. R2 is source 2. R2 is 0, 1, 0, right? Literally number 2. Destination, I want to write it back to R0, so this is 0, 0, 0. So what is my instruction? 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, and 0, 0, 0. All right, so that's it. That's my 16-bit instruction for add R0, R1, and R2. And I can use this trick for the other instruction as well, right? So you can use this trick to implement your ISA. All right, so that's what we're going to leave today with. We'll continue on with the material next week. All right, so any questions so far มีคำถามไหมครับ